Okay, welcome everybody. So my talk will be about a scalable multi-language data analysis language, which runs on Erlang. And to tell a little bit about myself, so I'm a PhD student at the Humboldt University in Berlin. I'm in my 4th year. I'm looking forward to finish it soon. And I am working on the Cuneiform workflow language, which is, as I said, a language for large-scale data analysis. And the major area of application of this language is in bioinformatics. So the data analysis workflows we will look at are from bioinformatics. And what I hope to achieve in this talk is, first of all, I want to give you an introduction to what Cuneiform actually is, what it does, what it feels like, and I hope to explain to you how one can implement large-scale data analysis programming languages, how you do this in Erlang, and why you would do this in Erlang anyway. Why Erlang is a very good platform to do this. And so, first of all, I want to introduce you to the term of a scientific workflow system, because when you want to do large-scale data analysis, your go-to kind of programming model would be scientific workflows. And a workflow is essentially a graph, a directed acyclic graph, in which the nodes represent tasks, and the edges represent data dependencies. And as you can see here in this upper example, these tasks can be very heterogeneous. So some of them may be Perl scripts or R scripts or even Java programs. So you don't have any guarantee about you can't afford to stick to one programming language in order to build these kind of workflows, because what you want to do is you want to reuse your software. So most of the time, the scientific communities are spread all over the world. Everybody has their own favorite programming language, and you can't force everybody to use the same language. And what you end up with is this kind of sometimes large dependency graph, which you can parallelize and distribute over many machines. And to make an example, so here we have a workflow that is consisting of 3 steps, and the first step takes 2 input files, and the data is processed in these 3 steps. And the first challenge, or the first also opportunity that is prevalent here, is that for bioinformatics, especially for next generation sequencing, the costs of sequencing genomes is constantly dropping. So this is a logarithmic scale, and we see here this line is Moore's law, so a halving in sequencing costs every 18 months. And we see here that the sequencing cost drops even faster than Moore's law. And this means that we are constantly facing larger and larger amounts of data which are generated cheaper and cheaper. And also, if you look at the kinds of machines that produce these sequencing data, it's easy to imagine that you can run many sequencing machines in parallel. So what you want to do is, if you are able to sequence in parallel, you also have to do the data analysis in a parallel and distributed way. And the third challenge is, this is kind of hard to see, but this is a screenshot from a website where tools for bioinformatics are summarized. And there's a huge amount of tools which are used in this kind of setting. So you can't hope to re-implement everything in a scalable way. You have to deal with whatever the bioinformatics community gives you. And the trick is then that you most of the time it's possible to partition the data, the input data, and parallelize all the tasks and run them distributedly. And this is what Cuneiform is for. So if I have to summarize what Cuneiform is in one sentence, I'd say it's a functional language for large-scale data analysis, which is implemented in Erlang. And if you compare it to other distributed analysis frameworks, what for example sets it off from systems like Spark is that it has a standalone, it has its very own syntax, so it's not a fluent API in Scala, and most importantly, it integrates different programming languages like Perl, like Scala, like Java, like R, so that you can reuse software that is already written in these kinds of programming languages. And it is also different from the kind of go-to workflow languages that you would use in this setting, because it doesn't depend on a static dependency graph, which it is traversing, but instead it is reducing a functional expression. And in functional programming, we have a richer, this is a richer programming model than just a static dependency graph. So the kind of recipe that Cuneiform follows is it's functional programming combined with foreign language interfacing. And the functional programming part is so important that I want to reiterate on this. So what we gain from functional programming is two things. First of all, we get a programming model that is very, very expressive, in which you can express all kinds of programs. It has natural operations on lists like map, cross product, dot product, all this kinds of stuff, which is very important when you want to do data parallel, when you want to iterate over lists. And it also has a natural way of expressing iterative algorithms through recursion. So what we gain here on this side is that we have a very general way to express how a large-scale data analysis program can look like. And the other thing that we gain from functional programming is the possibility to automatically find out what can be done in parallel. What can be done in parallel. So in functional programming, when you have an expression that is combined of sub-expressions, it doesn't matter in what order you evaluate the sub-expressions. And if it doesn't matter in what order you do it, you can also do it at the same time. And from this, we can automatically derive from a script that you give us, without the user having to do anything, what can be done in parallel and what not. And the other part is the foreign language interfacing, which I will be explaining with an example. So this is a very, very simple example of it says def task here, but actually what you're defining is a function. And it has the name gunzip, because we will be extracting a file from a compressed format. And it will produce one output file, and it ingests one input file, gz. And now what I can do is I can jump out of Cuneiform, and for every function that I want to define, I can always say, okay, this will be in Bash, this will be in Python. Now I'm going to R. And this way I can easily integrate libraries and tools that are already there. So in this file, in this case, I will bind the value of the out variable to the name output file, and then I will call gzip. -d means decompress, -c means write it to the standard output, and here I'm reusing the input parameter. and then I will pipe it out to output file. And then the system will know that it will have to look in the out variable for the name of the output file that was produced. And if I want to call this kind of function, I do this like normally, as a function call where I bind the argument gz to a concrete file. And what is done is, in this kind of graph, you see that you have here an input file. It is an operator is called on that, and an output file is produced. And now what I can do is I can easily extend this example to extract 3 files, because I can easily just bind a list here, and it will automatically know, okay, these 3 operations do not depend on each other, so I can run them on 3 different machines if I have them. Questions so far? Okay. And from this, I can assemble quite complicated workflows. And on the internet side, you can look up several examples from bioinformatics and next generation sequencing. We have, for example, a variant calling workflow, methylation analysis, and an RNA-seq analysis where we compare expression levels, and also kinds of other workflows that are variants on also already existing workflows. And if you look them up on the internet, what you always get is a chef cookbook, which helps you to set up this workflow. So essentially, what you have to do in order to run these examples is you just download this cookbook, and then you can create from this a virtual machine, and it will install all the tools for you. It will install Cuneiform for you. It will download all the data, and all you have to do is run the workflow, and it will give you the result. So it's pretty easy to get started. And when I started out in 2013, when I began my PhD, there was a blog post which with the title "Flow-Based Programming and Erlang Style Message Passing: A Biology-Inspired Idea of How They Fit Together." So this is essentially a workflow about how well Erlang fits the world of large-scale data analysis. And I wish I had known this blog post back when I started out, which I didn't. And so I had to learn the hard way how large-scale data analysis programming languages were built, and also the hint that Erlang is a good idea to do this in is something I only learned much later. And essentially, what this article is about is the observation that a large-scale data analysis system is essentially a 2-tier computational system. And on the one hand, there is you have the system level, the algorithm level computation, which does the heavy lifting, the number crunching, which has to be very, very fast. It doesn't matter if it is parallel or not. It can be also sequential, and the computation is only very local. And the other component is the organizational level, where you synchronize the computation, where you make the system wait for the input data to be produced, so that you can start the consumers, where you organize how the communication with the distributed file system is, the scheduling, and so on and so on. And what he did there in this post was he compared it to the way that a cell does the way a cell transcribes and translates genes inside it, which is very, very fast and very, very efficient, yeah, let's say, computational machine. And the other side was how cells interact through hormones and the cell-to-cell signaling systems, which are perhaps not that fast, a lot more stochastic, but they make the cells function as a whole system. And he observed that these two-tier yeah, let's say organizational levels also exist in nature. And what is perhaps the most important take-home message, that Erlang is a very good fit to do here the workflow level, the organizational level thing in workflows. And let me show you just as an overview how the architecture of an overall workflow system could look like. So on the top level, you have here these queries, which could be several workflows that are running at the same time, and they all talk to a cache. So when they have to produce partial results for their workflows, they first ask a cache, and if the cache already has the answer, then it will answer this from the cache and will not talk to anything else in the system. But if it has to, because the answer is not already there, then it gives the task to a scheduler, and the scheduler makes sure that the workers get informed and can produce the results. And only here, down here in this very bottom level, we have the actual number crunching and the fast computation going on. And also here it is where the bulk of the data is where it is produced, where we communicate it to a distributed file system. So the upper levels here never have to do any heavy lifting in the computation, and also never have to send around large amounts of data. This all happens down here in this kind of level. This picture is very nice to understand how a distributed workflow system could be set up, but it doesn't actually tell you what is difficult about designing workflow systems. So here I like this. Oh, this is very hardly readable. So here in this upper box it says execution environment. So what I'm trying to say here is that there is two things that are hard to do in distributed languages, programming languages. The one thing is that a workflow expression is an actual program and is written in a programming language. And if you want to do a proper programming language, then you have to model it, and there is a whole lot of literature and difficulties we could have there. And what is more, in the execution environment, which is essentially all the rest, this is a distributed system, and distributed systems are, as you perhaps know, also kind of hard. And now I want to look at each problem isolated. So how do you model a programming language? This is kind of the first important question. And it turns out there are several ways to do that. And at some point you have to decide for some method and follow this along. And the way I have done this for Cuneiform is, so essentially you have two specifications for a programming language. The one is the specification of the concrete syntax, which you give in a Bacchus-Naur form. I don't know if these terms are familiar to you, but what you can do from this kind of specification is you can generate a parser automatically from that. This is kind of a very, very well researched area. So parser generators are very well understood, and I don't understand them, yeah, but other people are very good at that, and there's really a lot of useful software out there. And The other thing you need is a semantics. And only when you have a semantics, you can actually formalize what the interpreter does. Yeah, I mean, you can sit down and program it from scratch and never have any problem with that. But it turns out that it's very, very hard to come up with a with an interpreter for a decently for a decent programming language if you don't have this kind of semantics. So yeah, two things: the specification of the syntax and the semantics. And how the semantics works is, essentially, you have an expression in a language, and the first thing you make up is what can an expression be? Yeah, and an expression in this case can be a string literal, a variable name, a future to a computation that that has started but not but where the result is not known yet, a conditional like an if-then-else expression, or a function application. And function applications can be either native, like where you stay in Cuneiform, or they can be foreign, where you switch to another language like Python or R or something like that. And this is a description of how each and every expression in Cuneiform can look like, and there's nothing more. Yeah? This picture shows already everything. And then you go through this and say, okay, when my expression has this in this form, what do I have to do in order to transform it to a slightly reduced expression? And you follow this process until you cannot reduce the expression anymore, and then it is in normal form, and you terminate the interpreter. And this kind of thing, when you describe an operational semantics, is essentially it's a text. Yeah, it's a description of how an expression can be evaluated. And here I want to show you how this can look like in the text form. You have a description, as I said, and for each and every like statement, you can have an inference. So you describe the evaluation in terms of inference rules, and these inference rules tell you how the evaluation is done. And essentially, you end up with a number of formulas. I'm sorry, you can probably not read it, but what I want to show you is that each and every formula that appears here in this paper, in the text, has a correspondence, a one-line correspondence in Erlang. So you have very neatly, you can say, okay, this is just a line of formula in the text, and it corresponds one-to-one to a line of code in Erlang. And this is something you don't get from most of the languages around there. So if you try this with Java, you will not get this one-to-one correspondence. But with Erlang, it's very very nice to come up with a model implementation for what you have described here in text. And right now, so when you have come up with an operational semantics or a semantics in general, then it's very easy to also create interpreters in other programming languages like Java, like Python. And right now, I'm maintaining also a Java version of this thing. But when I didn't already have this, it was a very valuable thing to have this one-to-one correspondence, because I could immediately try out an idea I had, like on the scratchboard, and it was very directly implemented, and I could try out what the language would do. And so this was a back and forth process, and in the end I ended up with something I knew that it would work. And only afterwards, now that the semantics is finished, it's actually feasible to go into other languages that are more verbose or slightly more difficult to find this correspondence. But it's not hard. Yeah, for the design process, it was very valuable to have Erlang. And the other component that is difficult about this kind of distributed data analysis system is the execution environment, essentially the distributed system that it is. And now the question is, how do you model a distributed system? And if you're from the Erlang world, you probably are a little bit biased towards the actor model. But if you use OTP, then you're probably familiar also with the finite state machines and stuff like that. These are all very valuable models for modeling systems. And for Cuneiform, I have decided to look at a system, an approach called patrinets. I'm sure everybody knows patrinets, but the advantage of patrinets in this kind of setting is that it's a very mature theory where you can reason about all kinds of properties like liveness, and you can find invariants and traps and code traps. And what is also very advantageous is that the decision making and the synchronizations are always very local in the net. So if I look at one transition, I always have to only consider the preset of this transition to know whether this transition is enabled or not. I don't have to look at the whole system. And also, when I look at distributed runs of the system, I can always tell which of the transitions fire independently. And if they fire independently, then of course I can do these things concurrently. And also here, Erlang is a very good programming model because concurrency is very doable. And here I want to show you a patrinet model of the execution environment. I'm going a little bit into this, yeah. So when a function is applied, essentially the function application appears here. And if the function application has already been seen in the system, then you can just look up in the cache what the result is and return the result. And if it's not the first time, if it's the first time that the system sees this function application, it will have to submit it and then the function application appears here. And what happens next is that a machine is scheduled to this function application, and then it goes out of the system where it is computed. This is where the number crunching happens. And also, when we take a machine out here, it appears here. So this means that the machine is that is occupied. And after some time, the computation happens. We might see the result here on this place, in which case the machine is released again and appears here in this in the ready pool. The result is put in the cache and is also communicated to the workflow system. So, and what I wanted to show you here is that a patrinet that fits on one slide can exhaustively describe all these features like caching, scheduling, partial failure, and all these things. And so this is a very dense way to describe this, and exhaustive. And sorry. Now you don't have patrinets in Erlang, but what do you do when you don't have a patrinet library in Erlang? You build one, and this is also what I did. So there's an OTP library that does patrinets, and you can look it up. You can give me feedback. You can it's kind of work in progress right now, but this is the way I'm intending to implement these kind of models in the Erlang world, where you yeah. And going back to this blog post of Samuel Lampe, you need programming languages to do the heavy lifting, and they are always most of the times they're system languages where you can do the heavy lifting very efficiently. And this is where Cuneiform goes out and employs other languages, and also what I just showed you, these two models, the operational semantics for the language and the patronets for the distributed system, they are all for the organizational part. Yeah, so in the analogy, in the biology analogy, the communication among cells, and also there's two reasons why large-scale data analysis is hard, and the one is because programming languages are hard, but I've shown you how you can model these, and the other reason is because distributed systems are hard. But Erlang is a good fit for both, because the functional programming paradigm is already very close to the operational semantics, which I use to model the programming language, and also because it's not hard to get the patronets out of the programming model of Erlang. It's already also very close. So this is, from my experience, why Erlang is a very good fit for the organizational part in large-scale data analysis. And this was a very concrete overview that I gave you here, and how we modeled these kind of problems. But I guess the blog post is much more general, and yeah. And to come to a close, Cuneiform is this language really exists. It has a REPL. You can call it up and play around with it. You can just download the binary on the website. It's just a few kilobytes big. And to summarize what it does, what you get is the combination of a functional programming language and very versatile foreign language interfaces, so that you can jump out and back and forth. It runs on, I didn't really say this, it runs on multiple distributed job queues, for example, HD Condor and Hadoop. You don't have to bother about parallelization. The script gets analyzed, and the parallel pieces of work are derived automatically. And you have a very expressive way to express workflows, and a lot of languages that you can interact with. For example, Bash, Perl, R, Python. And this is where I close my talk. Thanks for the attention. Questions? Okay, there is a question. So the question is whether there's how did we implement this on Hadoop? Is there a Hadoop library? And this is true. So the way you do this on Hadoop is, so Hadoop was originally for the MapReduce programming model, right? But recently, Hadoop has opened up its kind of programming model with the release of Hadoop Yarn. It is now possible to put any kind of programming model into Hadoop. And in our group, there's a very interesting project called Highway, and this is essentially an implementation of an application master for Hadoop that runs scientific workflows. And the scientific workflow languages it supports include Cuneiform, what I just showed you. But there's also other ways to run these workflows distributedly. But on Hadoop, you have this Highway application master. You have a question?
Yeah. How are you calling out to the other languages? How are you interfacing?
So the question is how we interface to other languages. So essentially, we open an Erlang port where we run the body of the script that you gave us. And the body of the script is not enough. So what you first have to also do is you have to bind the input variables to the arguments that were given in the function call. And what you also have to do is you have to collect the output variables again, so that you can send them further on downstream in the dependency DAG. And of course, when you ingest a file and output a file, this also has to come from the distributed file system and also has to be staged out to the distributed file system. There was another question? What was the first part? So right now we're not using distributed Erlang. We're using either Hadoop or HD Condor to do this. But with the models I just showed you of the distributed system, it would be very, very easy to do this also with distributed Erlang. But we haven't done this yet. This is still future work.
So Erlang runs on one node.
So exactly, if you run it only on Erlang, then you only get a single node setup. But if you want to run it on HD Condor, for example, then it also runs on Erlang. But the part that the handling of the job queue, the scheduling, the staging out and staging in of the data, this is handled by HD Condor. But it's feasible to do this in Erlang only. But this is has not been done yet. Again?
Your OTP, Petri library, what license are you using?
Apache. So the question was, what is the license of the PetriNet OTP library, and it's Apache 2, so no strings attached. Yes. So the question was, do we generate code from the model? Because a PetriNet is a model and not a library. So so this generic PetriNet library that I give you allows you to define transitions and places, and it will orchestrate the occurrence rule and the consumption of the tokens and the production of the tokens in other places for you. So you have a way to programmatically express the structure of your PetriNet. Yes, we don't have that. So the analysis of the PetriNet and the derivation of the properties and all that stuff, we don't offer. We just offer you so in this generic PetriNet library. Perhaps this is something we can add in the future. I don't know. But right now, what you can do is you can express your PetriNet and you can run it. But if you want to analyze it and reason about the properties, you have to stick to other frameworks, other tools. Other questions?